We're all tired, but let's get to it. Okay, so last time we closed with the proof that the real numbers were complete, right? We closed with the proof that theorem about compact metric spaces being complete, and then we used it to deduce that the Euclidean space was complete, right? And so for here until the end of the chapter, we're going to be dealing with sequences in the real numbers. Okay, so like up until this point, it's basically been sequences in metric spaces, and now we're going to talk about sequences in R. Okay, and we're going to start off with something pretty simple, which is so-called the monotonic sequence theorem. Okay, so definition, we call a sequence increasing if as you know, we call a sequence increasing if a sub n is always less than or equal to a sub n plus 1 for all n, right? For n and n, right? If I say strictly increasing, that means that it's then it's not less than or equal to, but it's less than, right? And similarly for decreasing. Similarly for decreasing, and all these sequences are called monotonic sequences, right? So strictly increasing, strictly decreasing, they're all called monotonic sequences. All called monotonic sequences. Okay, and one thing that we've seen before is that if a sequence is convergent, right, then the sequence must be bounded, right? So that's something that we've seen before. It's definitely not true that bounded implies convergent, right? Bounded does not imply convergent. Okay, but in the case of monotonic sequences, that is true, right? If it's convergent if and only if it's bounded. So that's the so-called monotonic sequence theorem. Right. So if a sequence is monotonic, then it converges if and only if it is bounded. And of course, we have one direction we already have, right? And so we only need to prove the reverse direction. Okay, so maybe just for warm up, think about this for a minute. You can probably prove it. Think about it for a minute, and then talk with a neighbor.
That's the thing that I make it. Yeah. So I'm convinced it's true, but there's
Well, it's always increasing, but it's never past a certain number. It will at some point approach some neighborhood and stay within that.
I know that.
Okay, so right, you have a sequence. It's bounded. Let's like for simplicity, without loss of generality, let's assume that it's increasing. Okay, it's increasing and it's bounded above, right? Right. There's some upper bound for its values, right? Okay. Anybody have an idea of what how we can show that it has to converge? What do you think it's going to converge to? The upper bound. Well, the upper bound, could be something like this, right? Maybe right. There's a lot of upper bounds, right? So, but the least upper bound, exactly, right? So that's going to be our claim, right? That so let so A sub n is bounded above. So let L be the least upper bound, but L be the least upper bound of the A sub n, right? And we claim that actually A sub n converges to that. Right? So we have to show, right, what does that mean? That given any epsilon neighborhood of L, there's a time past which everybody stays inside there. Right? So given any epsilon neighborhood of L, there exists a time past which all A sub n are in that neighborhood. So okay, right, so here's L. You choose some epsilon. It's increasing. This thing is the least upper bound of all these values, right? And so how do we know that there's a time? How do we know that there's a time past which everybody lies inside the neighborhood? Read it down. No? Okay, it's okay. Yeah, you guys are always the same group, same crowd. Nobody wants Charlotte? No? But
so is it because like it's the least optimal, so like there must be something that's like in between L minus epsilon and L?
yes, right. So you know that there's got one of these values has to be inside there, right? If there's no value, if there's no value between here and here, then L minus epsilon would be an upper bound for everybody, right? So there must be somebody who is greater than L minus epsilon, and of course smaller than L, right? So since L is the supremum of these values, we know that there must be some A sub capital N, such that A sub capital N lies inside of is bigger than L minus epsilon, right? Because if nobody's bigger than L minus epsilon, then L would not be the least upper bound, right? Otherwise, L minus epsilon would itself be an upper bound. well, take capital N to be capital N, right, to be this thing, right? That capital N, so then, for all little n bigger than that capital N, we know that, because since the sequence is increasing, we know that all little n's are going to be bigger than that guy, and of course they're going to be smaller than that, right? And so, and all of those guys, right, all the a sub n's are going to be between L minus epsilon and L plus epsilon. Right. Here's where we use the increasing, right? Okay, so indeed, given a epsilon, we're able to find a time past which everybody's going to be in the epsilon neighborhood. Okay, so the limit is L. Okay, I hope that seemed pretty straightforward. Okay, so yeah, any questions about that? Any questions? Okay. Okay, so now we're going to introduce a useful variation on the notion of limit. There are two things. They're called the limit superior and the limit inferior. Usually we call it lim sup, and then lim. It's sometimes written like this: lim with a bar over it, lim with a bar under it. Okay, those are all the same thing. Okay, so I don't know if I need to say this, but just for notation, like if you have a sequence and it is such that no matter what n is given, there exists a time past which all a sub n exceed that n. Then we write a sub n goes to positive infinity. Okay, so like converging to infinity. Like previously when we talked about convergence, we meant that there was some finite number that it converged to. But it will be useful to talk about sequences converging to infinity. Okay. So here's the definition of the lim sup. So given a sequence, a sub n, let E denote the set of all subsequential limits. Of that sequence. Okay. So you take that sequence and you look at all the subsequences, okay, and you say, you know, what are the limits of those subsequences? You put those guys in a set. That set is E. Okay. Some of those guys may be infinite. You may have subsequences converging to infinity, negative infinity, whatever. So this E sits inside the extended real numbers. Okay. And then you define the lim sup of the sequence as the supremum of E, and the lim inf is going to be infimum. Okay, and that might be infinite. Okay, if there's, if you have some sequence that goes off to infinity, then you count the supremum to be infinite. Okay, so just for a very, very simple example, right, if my sequence is -1 to the n, right, so it just bounces back and forth between -1 and +1, right, then the only two subsequential limits, right, E then is going to be just these two values, -1 and +1. The lim sup is going to be 1, the lim inf is going to be -1. Okay, so you just you look at all subsequential limits, right, and then take the supremum, right, so the lim sup is 1, lim inf is -1. Yeah, here's it.
What's the subsequential limit?
So limit of subsequences. So like, so basically you say take all subsequences of that one sequence, right? You've got your one sequence, and then you just take all possible subsequences, okay? And then you look at all the limits of those subsequences, right? The set of limits of all subsequences, I guess all convergent subsequences. Right, so you look at all subsequences that have limits, and then that's it. Yes, Krishi.
And these are convergent, including convergence.
Yes, yes. Okay. Okay, so remark that unlike the standard limit, unlike the standard limit, the lim sup and lim inf always exist. Does that seem plausible? Why is that believable? Why do we know that this is always going to exist? Well, suppose you look at the collection of values of A sub n. I'll let you think about it. Think for a minute and see if somebody can explain it to me. Why does the lim sup always exist? Talk to a neighbor. White, go ahead, yeah.
Well, so by the Bolzano-Wire stress theorem
Yes.
says that if there's always a convergent subsequence, so there's always E is always non-empty, so it has to be bounded in the synthesis in R. And I'm kind of lost.
You're close, you're not far off. You need to say one important thing. One or two important things.
Well, what I think was that since E is, and to the extent of real numbers,
Yep.
the supremum and infimum will always exist. So the only question would be if it's like empty. But I think even then we would call that infinity. So I guess it's just like even though the sequence might diverge, something will either be like periodic in it that we can get a convergent subsequence from, or explode off to infinity, which would still count.
Yeah, so like, the thing that's a little problematic is the empty set that you mentioned, right? So like, is it possible for the set of subsequential limits to be empty? Can anyone see why it's not possible for it to be empty? Okay, so let me say. So here's maybe one way of thinking about it. You say, well, look, this set E. No, not this set E. Consider the values. Right? Consider all the values of the A sub n, the values. Okay, it's either right the set of values. Right, it's either bounded or unbounded. Right, it's either bounded or unbounded. Right, if it's bounded, Bolzano-Wire stress, right? If it's bounded, that means that your sequence is actually inside of some compact set. So it's going to have a convergent subsequence, right? So that's good. So Bolzano-Wire stress does it for us, right? If it's unbounded, well, if it's unbounded above, that means that you can create a sequence that goes to infinity. If it's unbounded below, you can create a sequence that's going to negative infinity. So that's it. Okay, so we have these kind of something that's kind of like the limit, but always exists. And what it's going to be useful for us, where it's going to come in really useful is when we start talking about convergence tests for series. Okay, so we'll have these tests where you have things in back in calculus. You had these things that said if the root test, the ratio test, this sort of thing. But it hinged on certain limits existing or not, right? And what we're going to see when we redo that is that if we replace the notion of limit with lim sup, then the test still holds. Not exactly, but at least in the case of the root test, the test will still hold. And so we have a test that always works, right? Because we'll always get a number out of it, because the lim sup always exists. Okay. So yeah, okay. So so we have this thing, and what we're going to do now is give you a different perspective on the lim sup. So characterization. Alternate characterization of lim sup and lim. this is another way of thinking about it. It's kind of useful. There is another way of thinking about it, but I'm not going to talk about it. Sorry. I wasn't running away. I'm not going to talk about that. No, I just wanted to shut the door. It was getting a little noisy. Yeah. Yeah. Yeah, I had one professor in graduate school who was this kind of extremely shy old man, and he would end every lecture right by the door, and he would run out. Like he would finish like right next to the door, and then just like dash out afterwards. Yeah, I don't remember his name, but yeah. Mathematicians, pathological. It's like the refuge for the weird. Okay. Yeah, once I was at a conference and a bunch of mathematicians just sat around and talked about weird people that they knew among the other mathematicians. Like, who is the weirdest mathematician that you can come up with? And one person that they came up with, who I will not name, they said, oh yeah, so-and-so was once invited to X's house for lunch or something like that. But then X came to him later and he said, I'm sorry, I cannot invite you because I have only one spoon. Yeah, anyway, yeah. Okay. Yeah. Okay. So characterization of the limb soup. So here it is. There's sort of three parts of this thing. So the first thing is that the limb soup. So let is then be a sequence R. Let, as usual, E denote the set of subsequential limits. Right. Then when the limb soup of E the limb soup of A sub n actually is in E. Okay, so the limb soup is itself a subsequential limit. Okay, and 2, given any epsilon, there exists an n such that if you're past that n, A sub n is less than or equal to, less than limb soup. This is kind of bad notation. Limb soup. If k is bigger than n, then everybody past that point is less than the limb soup plus epsilon. Okay, so, right, like, if you're talking about the normal limit, right, if I'm talking about the limit of a sequence, right, suppose this is the limit of the sequence, then you know that given any epsilon neighborhood, there's a time past which everybody's in the epsilon neighborhood, right? So this is kind of like half of that condition, right? It just says that if this is the limb soup, then given any epsilon, there's a time past which everybody is below that. Okay, everybody's below that. And similarly for the limb inf, right? If this is the limb inf, then given any epsilon, there's a time past which everybody's above that. Okay, and so what does that tell you? You see that, each of this is sort of half of the condition of the limit, right? And if the lim sup and the lim inf are the same thing, then you have a limit, right? Because then you would have the full condition, right? You would have that these points are the same, and you can trap it within the epsilon neighborhood of that guy. So yeah, so it's sort of like a half limit condition. Okay, and any point which satisfies 1 and 2 must be the lim sup. Okay, let's prove it. So let's prove that last point first. So the final point. Right. Suppose there are two things with that value, right? Let's say it this way. Suppose there's another point, L, with those two properties. No, I'm sorry. Let me say it this way. Suppose there are 2 points with those properties. Suppose there are 2 points P and Q with those properties. Okay, and let's say that P is less than Q. Okay, but then that actually is impossible, right? Because if P has the property and Q has the same property, right? I could take an epsilon that's smaller, such that P plus epsilon is smaller than Q, and then Q would not be a subsequential limit, right? So then you take if you let epsilon be Q minus P over 2, P plus epsilon, we know that there exists a time past which all a sub n would be smaller than P plus epsilon, right, which is smaller than Q. Right. So you'd be staying out of this epsilon neighborhood of Q past that point, and so Q is not a subsequential limit. Contradiction. Okay, so there can only be one point with this property, and we'll see that it is the lim sup. Okay, so let's prove 1 and 2. So we're going to break it into cases. Case 1 is where e is just negative infinity. Case 2 is where e is positive infinity. Right. So, sorry, where the supremum is positive infinity, where the supremum is negative infinity, and where the supremum is a real number. Okay, so the first two cases not particularly interesting. If the lim sup is infinity, if the lim sup is infinity, that tells you that there is an unbounded sequence. There's a subsequence that converges to infinity, and so that's it, right? That's just by definition, basically, right? Right. For this to be infinity means that there's a subsequent one of the subsequential limits is infinite, and so you have so this thing is a subsequential limit. Yeah, Rishi.
So is it the case that like if all we knew was that our subsequential limits just went arbitrarily high,
Mm-hmm.
that we could then construct a new subsequence that went off to infinity? Like if we didn't know that E contained infinity, but we knew that it went arbitrarily high such that its supremum would be positive infinity.
Oh, I see what you mean. Oh, yeah. I guess it's maybe it's more complicated than I'm. So let's think. Yeah, I guess maybe that's the way to do it, right? You say, so you would say, do we need to do that? Hold on, let me think. We use a set of subsequential limits. If the supremum is infinite, yeah, I guess so. Okay. Sorry, I'm not. That's right. So, yeah. Sorry. That's what I. Yeah. That's right. So you say, well, look. In that case, right? In that case, E has no upper bound, right? E is no upper bound, right? And we can construct a sequence converging to infinity. Yeah. Okay. Yeah, sorry. And then in the case where the lim sup, when the lim sup is negative infinity, that just, in this case, it's actually more straightforward, right? That it's what I was mistakenly saying for the other case. In this case, this literally means that there must be a subsequence going to negative infinity, right? So then you know, E can only contain the point negative infinity, right? So there exists a subsequence converging there. Okay. Thanks. Why?
In that scenario, would that mean that every single subsequence converges to negative infinity?
Everything that converges, yeah, every subsequence that converges would converge to negative infinity.
Okay.
Yeah. Yes.
Would we, but so in that case, the lim inf must also be negative infinity, right?
That's true.
So then we know it's convergent, so then all the subsequences converge?
Oh, that's true. Yeah, thank you. Yeah, Ollie.
Never mind. I got it now.
Okay. Okay. Now let's go to the last case. So case where the lim soup is in R. Okay, and so we're going to use the following lemma that says that that E is closed. Okay, that any limit point of the set of subsequential limits must also be a subsequential limit, right? So any point that's in the limits of the subsequential limits is in E already. Right. Any limit point of E is itself a subsequential limit. Okay, and do people see that once we have this, then so right, we're trying to show that the lim soup is in E. So do people see that once we have that it's closed, then we have that fact? Yeah, Rishi.
And so are we saying here it's closed in like R?
Mm-hmm.
Okay.
Yeah. Right. Right. We're trying to show that the lim soup of the A sub n is itself a subsequential limit. Right. This is the supremum of E. Right. But the supremum of E is a limit point. Is a limit point of E. So it's going to be what? So this is going to be E. Once we show that E is closed, then then the supremum being a limit point is going to be inside E. Right, it's either in E or it's a limit point of E. Yeah. Okay, so let's prove that. Okay, so we're trying to show that the set of subsequential limits is closed, right? So maybe I'll let you think about it for a minute or two. Try and prove it yourself. This is actually kind of similar to an argument we did previously, so you might be able to. You might be able to get it. You can probably get it. Or if you maybe try to just get the idea of it, like why this makes sense. Okay. This kind of like really, I don't even know how to describe this expression, as you know. Okay, turn to a neighbor and say it's clear, or
What did you say?
Since something is inside of that all of the inside of the
So for any if we do
that means it's
I tried to end up with I don't subsequences like if we were by contradiction, then like how we have something that's outside, I'm gonna need to be our
So we can maybe use
but then everyone
the end
every neighborhood, every
element of
and
that.
then you make points of that.
That's for our
Our subset, the subsequential limit in that neighborhood was actually like then become the limit. I don't know if that makes sense. I don't know if that works. Like I don't know if it like it feels like there's probably gaps in that,
The
but
supremum of all
that's what I
of
thought.
yeah, I think I have a front. I see the
You see the like the idea, you talk, but I'm not.
into the
Nearby
open balls corresponding to one over n and for them.
okay. Anybody recognize that this is pretty similar to something else that we proved earlier? Anybody remember something that's vaguely similar? You remember when we showed that the set of limit points and the set of limit points was contained in the limit points? It's pretty similar to that, right? So like this guy is a limit point, right, of the subsequential limits, right? So what is that, right? You know, given any neighborhood, there's somebody in there, but that guy is a subsequential limit, right? Right, given any neighborhood, there's somebody in there, that guy's a subsequential limit, right? Whatever neighborhood we take, there's somebody in there who is a subsequential limit. Because those guys are subsequential limits, right, we can find points of E that are, you know, points of E itself that are close to it, and we can choose them so that the indices are increasing, right? It's that we did something we've seen a similar argument before. Yeah. So let's see if we can write that down now. So given any sort of k in n, we know that there exists some e sub k in the 1 over k ball around P. Right, so let P be a limit point of E. Right, so we should, yeah.
That should be a punctured neighborhood, right?
Yeah, thank you. Right. So choose somebody who's a limit point. We know that whatever punctured neighborhood we have, there's somebody inside there. And we choose them so that the punctured neighborhoods are shrinking. Yeah, are shrinking. Now, Michael, you look like
I'll wait for
okay.
proof to finish.
Okay, sure. Okay, yeah. Okay, so now each of the EK is a subsequential limit. Of, you know, of the A sub n's, right? Right. So there's some subsequence A sub n sub k. I don't know how to notate this. There's some sequence, and there's some subsequence that converges to it. Of the A sub n converging to E sub n. Right? So, so we can choose some A sub n sub k such that the distance from E sub k to that guy is itself smaller than 1 over k, right? And the A sub n sub k, the n sub k is bigger than the previous one chosen. Okay, so you have properly we should do this by induction, but you see how this is how we would do it. Right, because we've got infinitely many guys converging to E sub k, so we can definitely choose one that's close enough, and we just keep on going down the list until we get one that's whose index is big enough. Yeah, Ali.
Wait, sorry, why does the neighborhood have to be punctured?
That's just because of the definition of limit point.
Okay.
So if we have like another point, so we take the epsilon neighborhood around P, and we have another point in there that is like Q that is that's in E, right?
Yeah.
Can we not like draw like a delta neighborhood around it that's it's called like epsilon minus the distance between them over 2?
Yeah,
so it's
yeah,
in
yeah.
there.
Mm-hmm.
Then we know that there is a point at which the sequence will be inside of that Q ball,
Sure.
which is thus inside of the epsilon ball of
Mhm.
P. Is
Yeah.
that not like the definition of being a subsequential limit? So then
Yep.
it's an E.
Yep. So yeah, but we need to remember we need to construct a subsequence that converges to P. Right? We're trying to show that the limit, that this P is itself a subsequential limit.
Yeah.
So we have to, so that would give us, that would give us a subsequence, and past a certain point, all elements of that subsequence would go into here. But what we need is to take the subsequences at each of the points that are converging to P, and then to sort of like diagonalize a subsequence out of them to get one that converges to P.
Okay, yeah. So you can't just like take a subsequence that works for something arbitrarily close.
No, because you get that one subsequence, and it would come close to. Oh, I see what you're saying. No, yeah, no, I don't see that. No, yeah, because you're kind of conflating the notion of limit and subsequential limit,
Okay.
right? This is a subsequential limit. It's something kind of harder to do than just. It doesn't suffice to simply get points that are inside the neighborhood. We have to get points that we have to construct a subsequence that converges to P.
Okay.
And the
so
way
you'd like to increase.
Yeah, that's this thing here. So right, so each of these things, right, like each of these things has, in turn, a subsequence converging to it, right? Each of these guys has some subsequence converging to it. And we're going to say, okay, I'm going to take this guy from here, I'm going to take this guy from here, I'm going to take this guy from here, and I create a subsequence out of those subsequences that converges to P. Yeah, that's what's going on. Yeah, Vitica.
Is every subsequential limit in A sub n?
What's it?
Like is every E sub k a value in the sequence A sub n?
No, it's a limit of a subsequence of A sub n. Right, so you have the A sub n's, you have subsequences of them,
Yeah.
and then the E sub k's are the limits of those respective subsequences.
So could they be?
They could be, yeah.
They could be, but they don't. It's
They're not necessarily.
Okay.
Yeah. Yeah. They're just limits. Yeah. We don't know if they're A sub n's or not. Okay, good. Okay, so right. So we create this sequence, right? We choose the E sub k's that are within 1 over k of P. Then for each one, we choose like a neighboring A sub n sub k. That's within 1 over k of E sub k, and has increasing index, right? And then, of course, you see that the distance from P to A sub n sub k is smaller than 2 over k, right? By triangle inequality, right? Distance of this guy to P is 1 over k. Distance from this guy to E sub k is smaller than 1 over k, right? And so these guys, so the A sub n sub k converge to P, and so P is P is itself a subsequential limit. Okay. Debating whether I should stop here. It would make sense to stop, but Okay, I'm gonna just stop here. Okay, so that's it for today. Yeah, I was thinking maybe to go into like, so Rudin gives a bunch of limits, kind of useful limits, most of which are proved using the binomial theorem. But I think I'll just start that next time.